Recording.
Dear colleagues, the talk today will be presented by Professor Bakhrom Omirov. He is from the Institute of Mathematics of the Uzbekistan Academy of Sciences in Uzbekistan and also in Harbin Institute of Technologies in China. The title is On the Uniqueness of Maximal Solvable Extensions of Nilpotent Algebras. Please, Professor.
Okay. Just a moment. Share the screen. Yeah. So, first of all, I would like to express my sincere thanks to Professor Veselin Grensky for inviting me to give a talk here, and also I proud that we got some result which I would like to present today. And moreover, it's a pleasure. I'm glad that here among of participants there are experts in Lie algebras, and not only Lie but other super algebras, Lie super algebras and Leibniz algebras. So okay, the title of my talk is on the uniqueness of maximal solvable extension of nilpotent Lie algebras. Okay. From the classical theory of finite-dimensional Lie algebras, we know that an arbitrary Lie algebra is decomposed into semidirect sum of solvable radical and its semi-simple subalgebra, so-called Levy subalgebra. And so Levy subalgebra, we know that it's is decomposed into direct sum of simple ideals which are already completely classified. That's why the study of finite dimensional Lie algebras reduced to the solvable algebras and the representations of semi-simple algebras. Okay, thanks to Maltsev and Mubarakjanov's results, the study of non-nilpotent solvable Lie algebras is reduced to the study of nilpotent ones and their special kind of derivations, so-called nil-independent. So therefore, the study of finite-dimensional Lie algebras is focused to nilpotent algebras and their derivations. Okay. The research of solvable Lie algebras comes from special types of, with some special types of near-radical comes from different problems in physics, and it was subject of various papers. So here they are presented, some of them, not complete list. And okay, since the description of finite dimensional nilpotent Lie algebras, it's an immense problem, so it's impossible to solve. And even till now, it's known the classification up to dimension 7 nilpotent Lie algebras. So and that means that only in low dimension they are completely classified. Okay, of course there are a lot of classification, but there with some restrictions on nilpotent Lie algebras. Okay, for instance, in a paper 13 here, the authors claim that they have found 24,168 non-isomorphic 9-dimensional nilpotent Lie algebras with a maximal abelian ideal of dimension 7. So that's why it's quite difficult to, so it shows that that's the description of all nilpotent Lie algebras is so the difficultness is come, so it's even this numbers shows that it's impossible. Okay, and realistic partial classification problem is to classify all solvable Lie algebras with a given Lie-radical of an arbitrary finite dimension n. So far, this has been done for certain series of nilpotent Lie algebras, like abelian, Heisenberg, Varel-Nil algebras, as well as certain filiform and quasi-filiform algebras. Okay. Okay. The point here is that non-nilpotent solvable Lie algebras can be reconstructed or described by using their Lie radical and special kind of derivations. The Mubarakjanov method of construction of solvable Lie algebras in terms of their Lie radical is effectively used. In 2010, Snobel, in his paper, he conjectured the following. The following conjecture was stated in his paper, and it's asserts that let n be a complex nilpotent Lie algebra, not characteristically nilpotent, and let there are two algebras, S and S bar, be solvable Lie algebras with the same Lie radical n, and they are of maximal dimension in the sense that no such solvable algebras of larger dimension exist. Then these two algebras, solvable algebras, are isomorphic. So in our, okay, so it can be reformulated in the following way, that up to isomorphism there exists unique complex maximal solvable extension of non-characteristic nilpotent Lie algebra. Okay, first, I would like to give some preliminary definitions and nilpotency and solvability. For a given Lie algebra L, we define lowest central and derived series as ideal defined as follows. So L1 is equal to L, Lk plus 1 is Lk multiplied to L, and L to the power 1 in brackets, it's just L, and L to the power S plus 1 in parentheses. So it's Ls multiplied to itself, okay? A Lie algebra is said to be nilpotent, respectively solvable, if there exists some natural number n such that ln equal to, such that L to the power n equal to 0. And in case of solvable, there exists m such that derived series stabilize in 0 in terms of m. Okay. Since the sum of finitely many nilpotent ideals is a nilpotent ideal, there exists a maximal nilpotent ideal called Lie-radical of the algebra L. Okay, an abelian. So derivation is a linear map, is a linear transformation of algebra which satisfies to the Leibniz rule. And the set of all derivations forms a Lie algebra with respect to binary operation commutator. Okay. And okay, definition. An algebra, an abelian subalgebra of n, the Lie algebra of derivations of the algebra of nilpotent algebra n, which is consist of semi-simple linear transformations, is called a torus on n. A torus is said to be maximal if it is not strictly contained in any other torus. And it should be noted that in case of complex number field, semi-simple means diagonalizability semi-simple isomorphism is diagonalizable. Okay, and moreover, from Mastov paper, so it's in okay, it is known that any two maximal tori of an nilpotent Lie algebra are conjugated under an the automorphism of the algebra, and consequently, the dimensions of two maximal tori of an nilpotent algebra are equal. Okay, and so let n be a finite dimensional nilpotent Lie algebra, non-characteristically nilpotent. And what does it mean, non-characteristical nilpotent? This is a special and huge class of subclass of nilpotent algebras, and they are characterizing by the property that all the derivation are nilpotent. And actually, there is no solvable algebra whose radical is characteristically nilpotent. Okay, that's why we are considered, when we talk about nilpotent Lie algebras, we always mean non-characteristically nilpotent. Okay, and we denote by rank of n the dimension of a maximal torus. And from paper of Meng, it's known that rank it's bounded from the above with the number of generators of nilpotent Lie algebra n. Okay, let T be a maximal torus of a nilpotent Lie algebra n, and here we have a root decomposition, root subspace decomposition of an algebra n, where root subspaces are defined as follow. And okay, and a maximal torus admits a basis T1 Ts which satisfies this condition T of n sub alpha j equal alpha sub ij and alpha j. And it is known that alpha sub ii, when indexes are equal, then alpha ii doesn't equal to 0. And if sub index is different, then this scalar is equal to 0. Okay. Okay, consider a solvable Lie algebra. It is semidirect semidirect product of radical and its maximal torus. And okay, t multiplication t by t is equal to 0 because it's abelian algebra, and n is given already. So we need to just define multiplication n by t, and it's given like action of t on n. Okay. In fact, the conjugacy of arbitrary two maximal tori t and t prime under the inner automorphism of n implies that algebras R sub t and R sub t prime are isomorphic. Actually, these algebras are okay. And next, we need the following definition. A solvable Lie algebra R with radical n is called a maximal solvable extension of the nilpotent Lie algebra n if its codimension n is maximal. Okay, this is the main object of our talk today. It is known that codimension of n doesn't exceed the number of the number of degenerators of the radical. Okay, and because Lie algebra, thanks to Lie theorem, the square of solvable Lie algebra is nilpotent, and that's why any solvable Lie algebra has non-trivial near radical. Of course, here we exclude trivial case. Okay. Therefore, for solvable Lie algebra R, we have decomposition into a vector direct sum of vector spaces. Here n is near radical and Q is subspace complementary to n. And the next proposition asserts that in case when R is a maximal solvable extension of n, then rank of dimension torus, maximal torus, is coincident with dimension of complementary subspace to n. Okay, so let's present first an example which shows that Snowball's conjecture, the condition of the ground field to be complex is essential. If we consider, indeed, if we consider three-dimensional Heisenberg-Lie algebra, then up to isomorphism, there exists unique complex solvable five-dimensional Lie algebra, which is given by this table of multiplication. And here, E1, E2, E3, they are base of H1, and X1 is X1, X2, it's base of complementary subspace. Okay. However, when we omit the condition of complicity of the ground field, for example, if we consider real numbers field, then appears two non-isomorphic maximal solvable extensions. They are the following. So it means that in Snowball conjecture, the condition of the complicity of the field, it is the condition that field is a complex numbers field is essential, and the existence of non-isomorphic two complex maximal solvable extension of with a given near radical was also present by Gorbatsevich, and that shows that conjecture of Snowball is not true in general. In fact, Gorbatsevich constructed two nine-dimensional complex maximal solvable extensions of the near radical, which is direct sum of seven-dimensional characteristically nilpotent ideal and the abelian one-dimension ideal. Okay, this is split case. And then the first algebra say is the direct sum of n1 and two-dimensional solvable ideal span to the x and e8. Okay, while the second algebra is a solvable extension obtained by the derivation adjoint x plus d, where d of e2 equal to e sub 7 is an outer derivation of n7. So the direct computation leads that this complex solvable Lie maximal solvable extensions are non-isomorphic. So something necessary to change. Okay, and let's find an example. Consider nine-dimensional nilpotent Lie algebra with the following table of multiplications, and direct computations lead that the all derivation of this algebra has the following matrix form. You see, it is upper trigonal trigonal form, and here we have a zero root, and alpha root has a multiplicity 4, and moreover we have tau here. Okay, and obviously near radical T span so is two-dimensional, where the T1 is diagonal matrix of this form, and T2 is diagonal matrix of this form. Okay. Straightforward computation leads at solvable Lie algebras that constructed as follows. Here, semi-direct product n with t is a maximal torus of n. Okay. And the second one is a semi-direct product n with t prime, where t prime is span t1 plus d t2, and where d is a derivation of n9 defined as follows. Actually, I can say that d is generated by this tau, mu, and delta, these parameters. Okay, we can choose some parameters. So d with non-zero, these parameters tau, mu, delta. Okay, then these two maximal solvable extension are non-isomorphic. And note that T1 plus D is non-nilpotent derivation, which is non-diagonalizable on n alpha, on root subspace. It's exactly this subspace. Okay, this subspace. Okay, based on the structures of maximal solvable extensions given in Karbatsevich example and example 1, we give the notion of we introduce the notion of the locally diagonalizable nilpotent Lie algebra. Okay, a nilpotent Lie algebra n is called the locally diagonalizable if restrictions and projections of all non-nilpotent derivation of n on each root subspaces with respect to a certain maximal torus are simultaneously diagonalizable. In case of this algebra, the definition delocally diagonalizable means that tau mu delta is equal to 0 should be and nu equal to 0, and mu also should be equal to 0. Okay. Proposition. Let n be a delocally diagonalizable nilpotent Lie algebra, then there is no root, root with respect to a maximal torus T on n. However, there are non-locally diagonalizable nilpotent Lie algebras with respect to a maximal torus that admits both 0 and non-zero roots. Okay, now we are ready to present the main result concerning maximal solvable extensions. Okay, there exists a unique up to isomorphism complex maximal solvable extension of a locally diagonalizable nilpotent Lie algebra, and it is isomorphic to the algebra A sub T, where T is some maximal torus. Okay, and example 1, as well as Karbatsevich example, shows the condition of locally diagonalizable in main theorem is essential. So from this theorem, we obtain the positive solution of Snowball's conjecture in the case of locally diagonalizable nilpotent Lie algebra. So we just need to add condition on the nilpotent Lie algebra. Just add here d locally. Sorry, it's misprint. D locally diagonalizable, and then the conjecture is true. Okay, what would be if let's n be a nilpotent Lie algebra such that there exists a basis of n such that all derivations of n in this basis have upper trigonal matrix form, and there exists a non-nilpotent derivation such that its restriction and projection on some root subspace n alpha, where alpha is non-zero primitive root, with respect to a maximal torus is non-diagonalizable, then there exists at least two non-isomorphic maximal solvable extensions. This proposition gives a partial answer whether this main theorem is true in reverse implication. I mean, okay. And based on existing numerous example and proposition above, we believe that the following criteria on uniqueness of maximal solvable extension is true. Namely, we have a conjecture that a complex maximal solvable extension of a finite-dimensional nilpotent Lie algebra is unique up to isomorphism if and only if its nilradical is locally diagonalizable. Moreover, it should be isomorphic to algebra A sub T. Okay, so now I need more definition because a more beautiful result appears with maximal extensions. Lie algebra is called complete if it's centerless and any derivation of algebra is inner. It means that it has any derivation is so has it's just operator of left multiplication. Okay, and non. So we have two propositions. First one states that a non-maximal solvable extension of a nilpotent Lie algebra admits an outer derivation. Second one states that a maximal solvable extension of an nilpotent Lie algebra, which is not locally diagonalizable, admits an outer derivation. Okay. And from these two propositions, we can formulate the following theorem. A complex solvable Lie algebra is complete if and only if it is a maximal solvable extension of the locally diagonalizable nilpotent Lie algebra. Moreover, from propositions above and the proof of this theorem, we can conclude that a complex solvable Lie algebra admits only inner derivations if and only if it's a maximal solvable extension of the local diagonalizable nilpotent Lie algebra. It means that the first, it's the criteria for solvable Lie algebra when the first group of homology in coefficient itself is trivial. It's some kind of analog of the first Whitehead's lemma. Okay, so we just proved that the nice maximal extension have the form A sub T, but how to construct this algebra? Okay, in general, RT does not describe all all maximal solvable extension of n, while in the case of locally diagonalizable n, thanks to main theorem, we obtain the description of all maximal solvable extensions. Okay, now it's a tool how to construct it. Assume, so let's E1, En be a basis of n. And here is the table of multiplication where Cijt is structural constant. And for ijt such that s sub j n to the power t doesn't equal to 0, we consider a system of linear equations. Alpha I plus alpha j equal alpha t when this structural constant doesn't equal to 0. So this is a system of linear equations in variables alpha 1, alpha n. Okay. And we denote by R in E1, En the rank of the system S sub E, and setting R of n as a minimum of the ranks, as a basis runs over all base of n, we know that for a nilpotent Lie algebra n over an algebraically closed field, we have the equality that dimension of maximal torus is dimension of n minus r of n, this invariant, okay? And let's fix that basis and consider the fundamental the basis of fundamental solution of the system SE, okay? Then the diagonal matrices of this form, they generate a maximal torus T of n, and thus we have solvable algebra R sub T as a semi-direct sum of n and t. Okay. So actually, there are several results on description of maximal solvable extension of local diagonalizable. So, and thanks to our main theorem, so some results given in this paper can be obtained in more shorter way. Okay, this is alternative method which we proposed. And the most complete description of solvable Lie algebras use various types of near radical are obtained till the present time is given in the book of Libor Snobel and Pavel Winternitz here, okay, in their monograph. Okay, actually, just recently we realized that the same approach can be used for the Lie superalgebras. For the Lie superalgebras, and now, if I have time, I briefly say that the same is true, but under one more condition, which is also essential. Okay, a Lie algebra is the two-graded vector space equipped with a bilinear bracket and which satisfy the following two-graded super identities. Okay, and a super derivation of degree d of a Lie superalgebra is endomorphism d with the property which satisfies this property. So if we denote by der of L sub S the space of all super derivation of degree n, then we have that two-graded subspace, and if we equipped on that space of super derivation the following bracket, then der sub L is a Lie superalgebra, where even super derivation is just derivations. So the torus is defined in the same way, but here we just to note that in case of complex numbers, diagonalizability of odd super derivation leads to its nullity. That's why we can assume that in the case of complex numbers field, a torus on Lie superalgebra L is a commutative subalgebra of Lie algebra, just Lie without super structure. So then we can use the previous results. Here so the conjugacy of two maximal torus is also holds true for superalgebra's case, because it's we consider even part of derivation, which is the Lie algebra. Okay, and consider a complex solvable non-nilpotent Lie algebra R with his even and odd part, such that square of odd part belongs to the square of even part, actually this condition equivalent to the the analog of Lee's theorem for solvable superalgebra holds true if and only if this embedding is true. So this is equivalent to fulfillment of analogy of Lee theorem. Okay. And as a consequence, the fact that the square of solvable Lie superalgebra lies in its near-radical. So again, we can decompose our superalgebra as a direct sum of vector space near-radical and its complementary subspace, which consists of even elements, even homogeneous elements. Okay. And the definition of diagonalizability of Lie radical is exactly the same as in Lie algebra case. And here, the main theorem just need one more condition. Okay, let's start. Under the condition that an analogy of Lie's theorem holds, there exists a unique up to isomorphism complex maximal solvable extension of the locally diagonalizable nilpotent Lie superalgebra, and it is isomorphic to an algebra of the type R sub T. Okay, the essentialness of the property the local diagonalizability follows from the Lie part, algebra part, and the condition for the fulfillment of analogy of Lie theorem is essential as well. It from the following example. Okay, if we consider nilpotent Lie superalgebra here with even homogeneous element x and odd homogeneous elements y, then it's clear that n is the locally diagonalizable nilpotent Lie superalgebra, and the fulfillment of the analogy of Lie's theorem for a maximal extension of n leads to the unique solvable extension to just this one, this algebra. While if we don't require the fulfillment of analogy of Lie's theorem, then up to isomorphism, there are two non-isomorphic maximal solvable extension of n. They're given by their own table of multiplications. So similar to the Lie algebra case, here's a table of multiplication of nilpotent Lie superalgebra, and the system of linear equation is given in a similar way, but just system would involve even and odd part. To even bias elements correspond variables alpha, and to odd bias elements correspond beta. So then we again the fundamental solution of the system, if we have, so if you compute the base of fundamental solution of the system S sub xy, then diagonal matrices forms a basis of maximal torus n. So again, we can we are able to construct algebra R sub T. Okay, and so this again to give alternative method to prove several of theorem 4.3 in this paper and another theorem in second paper. Okay, but in case, okay, that's, I think time is, I don't know to bother you with Leibniz algebra situation. This is another very natural generalization of Lie algebras. and situation over there, it's not well, it's not similar, because there exists example of nilpotent Lie algebra. There exists example of nilpotent Leibniz algebra, and maximal extensions are not unique. Even near-radical is the locally diagonalizable Leibniz algebra, but it's related sections of torus from right and left sides. Okay. So I think
Okay. We thank you very
I
much
have
for the nice
finished.
talk. Are there any questions or comments? If no questions, I would ask the speaker to send the presentation and to allow us to write, to put the talk with the video on the homepage of the seminar. I hope that you agree with this.
Okay.
So you send
To,
simply us the presentation
to whom?
to me.
Okay. I'll send it to you like
Okay.
after Zoom, after meeting. Okay.
Okay. Thank you very much.
Maybe I would like to comment that I'm happy that that odd conjecture of mine led to interesting research.
Okay, thank you. Noble.
Yeah, it's actually, that first we started to, so in 2004, in 2013, we extend the Mubarakjanov method to the Leibniz algebra case. And then we found some similar, some nice properties of complementary subspace. It was, and then we tried to generalize it, and only after that we found uh, Lieber's conjecture, and it was stimulated to us to pay more attention, and we tried to solve it, and finally, so it seems to me that it's solved now, but there is another conjecture with a pair with this solution, and also for the it's just I sent the title of my presentation maybe 1 month before, but working actively in this area, we just realized that all techniques can be extended for super Lie algebras. So it's amazing. Unfortunately, for the Leibniz algebra is not so clear now, but we are working on it.
Okay, thank you very much. Are there some other questions or comments? The next Friday there will be another talk, but it will be in the field of mathematical logic. So we inform soon the participants. Okay. Thank you very much once again.
I also would like to express my thanks to my supervisor who are among of participants, and also Vladimir Gorbatsevich, and my collaborator with whom I worked on this topic, Bulgarian Salijanov. Thank you very much.
Ами, завършваме където работи. Едно и също е това.